far beyond the planets, where the sun has faded into one bright star among many, Voyager is still listening. Outside the heliosphere, its instruments have encountered denser plasma, unfamiliar magnetic conditions, powerful cosmic rays, and faint waves moving through the matter between stars. Some of those signals can be translated into tones, making the space beyond our solar system sound less empty than it appears. Yet Voyager may still be crossing a disturbed region shaped by the sun it left behind, rather than untouched interstellar space. So tonight, the question is simple. What did Voyager actually detect after leaving our solar system? And what does it reveal about the darkness between the stars? Before we begin tonight's journey, subscribe if you want more calm space documentaries like this. Leave a like if you enjoy deep space mysteries. And here is a question. If Voyager could make only one final measurement before falling silent, what would you want it to search for? Let me know in the comments. I will pin the most thoughtful answer. Tonight, you are watching the Just About Space channel, talking about what Voyager detected after leaving our solar system. For most of its journey, Voyager 1 was still moving through a place shaped by the sun. The planets had disappeared behind it long ago. Jupiter and Saturn had become memories, stored inside aging instruments and photographs, sent home decades earlier. The sun itself had shrunk into the brightest star in a dark sky, too small to fill a window, and too distant to offer warmth in any ordinary sense. Every second, the sun releases a stream of charged particles that expands outward in all directions. Near Earth, this solar wind races past our planet at hundreds of kilometers per second. It carries the sun's magnetic field through space, fills the region between the planets, and creates an enormous bubble around the entire solar system. That bubble is called the heliosphere. It is not a solid shell. There is no visible wall, no bright line, and no surface a spacecraft can photograph while crossing. The heliosphere is a moving region where pressure from the solar wind pushes outward against the thin material between the stars. Even after passing every major planet, the spacecraft remained surrounded by particles that had begun their journey at the sun. This is why leaving the solar system is more complicated than it sounds. The planets do not end at one clean border. Beyond Neptune lies the Kuiper Belt, filled with frozen worlds and ancient debris. Farther still, the distant Oort cloud may extend thousands of times beyond Earth's orbit. It crossed the region where the solar wind could no longer push outward strongly enough to dominate the surrounding environment. That boundary is called the heliopause. On one side, the space around the spacecraft is shaped mainly by the sun. On the other, it is shaped by the material between the stars. This was the border Voyager was built to find, even though no one knew exactly where it would be. The solar wind does not expand into a perfect vacuum. The solar system is moving through a thin cloud of interstellar gas, and that surrounding material presses inward against the heliosphere. Its activity rises and falls. The pressure of the solar wind varies. Magnetic fields twist and reorganize. The heliopause can move inward or outward over time, almost as though the solar system is breathing slowly through the galaxy. Voyager approached this uncertain region without a clear map of its shape. Its original mission had been designed around the giant planets, not around a crossing that would happen billions of kilometers later. Some instruments had failed or been switched off. Power was declining. The radio signal took many hours to reach Earth. As Voyager moved outward, the environment began to change. Particles from the sun became less common. High-energy particles arriving from the galaxy became more common. Magnetic readings shifted in ways that were difficult to interpret. There was no single dramatic moment when every instrument agreed that the spacecraft had crossed the border. Some signs suggested Voyager was close. Others created confusion. The spacecraft entered regions where solar particles dropped sharply, only to find that other measurements did not change in the way scientists expected. The edge seemed less like a wall and more like a landscape. There were layers, transitions, and places where particles behaved differently while the magnetic field remained strangely familiar. For a time, researchers were not certain whether Voyager had truly left the heliosphere or had entered one final region still connected to the Sun. It had to be reconstructed from invisible particles, magnetic fields, and weak signals sent by a machine too distant to observe directly. The spacecraft could only feel the local environment passing across its instruments and allow scientists on Earth to build the larger picture from those measurements. The strongest evidence came from plasma. Plasma is a gas whose particles carry electric charge. It is common throughout space, even where the density is so low that the region would feel like an almost perfect vacuum. Voyager carried a plasma wave system designed to detect electric fields and waves moving through charged particles. It did not need to collect the plasma itself. Instead, it could detect the way electrons in the surrounding medium vibrated. The plasma outside was much denser than the solar wind plasma Voyager had known inside the heliosphere. The crossing occurred in August 2012, although the strongest confirmation came later, after scientists studied plasma waves produced by solar eruptions traveling outward through space. Interstellar space contains no air a person could breathe, and almost no matter compared with any place on Earth. There are atoms, electrons, dust grains, magnetic fields, cosmic rays, and waves moving through the thin plasma. A few particles spread through each cubic centimeter can still shape the boundary of the entire heliosphere when they extend across light years. Voyager entered a medium that had been interacting with the solar system long before the spacecraft existed. The heliosphere forms partly because the solar wind pushes outward, while interstellar matter presses inward. What it found challenged the comforting picture of the Sun, surrounded by a quiet, empty ocean. Its particles could vibrate, its magnetic field had structure. Galactic cosmic rays moved through it, with far less resistance than they experienced inside the Sun's protective bubble. The spacecraft detected a sudden rise in these high-energy particles after crossing the boundary. They came from distant regions of the galaxy, accelerated by violent events such as supernova explosions and other powerful processes. Inside the heliosphere, the solar wind and its magnetic field reduced the number that reached the inner planets. Beyond the heliopause, Voyager entered a place where that shielding had weakened dramatically. Voyager had not merely traveled farther than any earlier spacecraft. It had moved from a region created by our star into one where the wider Milky Way became physically present around it. The darkness beyond the heliopause was carrying information from the galaxy. Scientists expected the direction of the field beyond the heliopause to differ more strongly from the field inside. Instead, Voyager found that the orientation remained unexpectedly similar for a time. Perhaps the field outside was being bent around the heliosphere. Perhaps Voyager crossed through a region where the two environments remained linked in ways simple models had missed. The edge was not a clean separation. The Sun's influence did not vanish at one exact point. Particles, fields, and disturbances continued crossing between the two sides. Solar eruptions still reached Voyager even after it entered interstellar space. Large events near the Sun could send waves outward through the heliosphere, and years later, those disturbances could reach the spacecraft and shake the surrounding interstellar plasma. The Sun was distant but not silent. Its activity traveled slowly across billions of kilometers and announced itself through the vibrations Voyager detected. This created an unusual connection. A major eruption near the Sun could occur while the spacecraft was far beyond the planets. The disturbance would travel outward for more than a year, cross the heliopause, and compress the plasma around Voyager. The probe would record the event. Its signal would then take many additional hours to return to Earth. Scientists could study the response of interstellar space to something the Sun had done long before. Voyager had become a remote listening station placed outside the solar system's protective bubble. From there, it could measure both the galaxy and the fading reach of the sun. The plasma wave instrument later detected something even quieter. Between the stronger events caused by solar disturbances, researchers identified a faint and persistent background signal. It suggested that the interstellar plasma around Voyager was producing a continuous, narrow vibration. This was not ordinary sound. Space remains silent to human ears because there is no atmosphere carrying pressure waves in the way air does on Earth. The signals had to be converted into frequencies people could hear, but the underlying plasma waves were real. Voyager had detected a steady feature of the interstellar medium itself. The space between stars was not only filled with particles, it had a background activity that continued even when the sun was not strongly disturbing it. This faint signal allowed scientists to track changes in plasma density over time. Voyager was moving through regions that were slightly denser or thinner, revealing structure inside what once appeared to be uniform emptiness. The differences were small. The environment was still incredibly thin. Yet the measurements showed that interstellar space has texture. There are gradients, compressed regions, and changing conditions. The emptiness has geography, although no eye could see it. For future spacecraft traveling much faster, this structure would matter. Gas and dust that seem harmless at Voyager's speed could become dangerous at a significant fraction of light speed. Magnetic fields could affect charged systems. Radiation would accumulate over years. Voyager's slow journey was beginning to map an environment that later missions would need to cross far more quickly. The probe was not traveling toward Proxima Centauri, and it would never reach another star as an active spacecraft. But its measurements belonged to the larger story of interstellar travel. Before humanity can send a machine across light years, it must understand the material through which that machine will move. Voyager provides only one narrow path through the local interstellar medium. It cannot reveal the full shape of the heliosphere, or every condition beyond it. Voyager 2 crossed the heliopause at another location and found both similarities and differences, giving scientists a second view of the boundary. Together, the two probes showed that the heliosphere is not perfectly symmetrical and that its outer regions change with direction and time. Still, two paths are almost nothing compared with the size of the bubble. The rest must be inferred. This is what makes the mission so unusual. The spacecraft is ancient by technological standards, but it is exploring a region that remains almost completely untouched. Its computers are weaker than ordinary modern devices. Its instruments were designed before many people alive today were born. Yet no newer spacecraft has traveled farther. Every measurement comes from hardware surviving far beyond its expected lifetime. The data is limited. The power grows weaker each year, but the location cannot be replaced. Eventually, Voyager will stop transmitting. Its nuclear power source will no longer provide enough electricity for the remaining systems. Earth will listen and receive nothing. The spacecraft will continue moving through interstellar space, but the environment around it will become unknown again. Its antennas will still point roughly toward a sun too distant to answer. Its instruments may remain physically attached, but without power, they will no longer turn particles and waves into information. The first human object to detect the interstellar medium directly will become silent inside it. For now, the connection remains. A weak radio signal crosses billions of kilometers and reaches antennas on Earth with only a tiny fraction of its original strength. Inside that signal are measurements from beyond the heliopause: plasma densities, particle energies, magnetic fields, and evidence that the space outside the sun's bubble is more active than darkness suggests. Voyager left the familiar environment of the solar system and found no empty void waiting beyond it. It found another environment. It found a thin interstellar ocean with currents too subtle to see. radiation arriving from the galaxy, and plasma capable of carrying waves from the distant sun. The boundary did not separate something from nothing. It separated one kind of space from another. And once Voyager had shown that the darkness beyond the heliopause was filled with moving particles, hidden pressure, and faint waves, the quiet signal inside that plasma became the clearest way to understand what the spacecraft was truly hearing between the stars. Voyager is not surrounded by sound in the way a person is surrounded by sound on Earth. There is no air beyond the heliopause, carrying voices, wind, or distant explosions. A human ear placed outside the spacecraft would hear nothing at all. Plasma contains charged particles, and those particles can move together in organized ways. Electrons can shift, return, and oscillate, creating electric fields that pass through the surrounding medium. The instrument does not record a natural soundtrack hidden in the darkness. It measures electrical activity, and scientists translate parts of that activity into frequencies that human ears can recognize. The original waves exist in the plasma, but the familiar sound is created only after the measurements return to Earth. Voyager is not listening for noise in empty space. It is detecting the movement of matter so thin that it cannot be seen, touched, or photographed directly. The pitch reveals the density around the spacecraft. When the plasma becomes denser, the natural frequency of its electrons changes. By measuring that frequency, researchers can estimate how many electrons occupy the space Voyager is passing through. The spacecraft becomes a probe, moving through an invisible landscape, using vibration instead of vision to reveal where the material changes. Some of the strongest plasma waves appeared after powerful events near the Sun. Solar eruptions can throw enormous clouds of charged particles into space. These disturbances move outward through the heliosphere, crossing the orbits of planets and continuing far beyond them. The disturbance presses against the interstellar plasma and causes the local electrons to oscillate more strongly. The strange tones later played on Earth are therefore part of a chain beginning near the Sun, traveling across billions of kilometers, crossing the heliopause, disturbing the plasma around the spacecraft, and finally returning as data through a weak radio signal. The spacecraft is outside the main flow of the solar wind, but it has not entered a region completely disconnected from the Sun. The Sun continues pressing against the interstellar medium from the inside, while surrounding material presses inward from the galaxy. For scientists, the strongest events are useful because they make the surrounding plasma easier to measure. A quiet medium can be difficult to study, but a disturbance forces the particles to respond clearly. The signal suggested that the interstellar plasma was producing a faint vibration almost all the time. It may involve thermal motion, weak plasma turbulence, or distant disturbances moving through the surrounding medium. Several processes could contribute to the feature Voyager detects. What matters is that the signal allows the plasma to be measured even when the Sun has not recently disturbed it strongly. As Voyager moves outward, small changes in the frequency reveal changes in density. The spacecraft can trace the local interstellar medium more steadily, rather than waiting for one powerful event after another. The results show that the space beyond the heliopause is not uniform. Some regions are slightly more compressed, others are thinner. The differences are tiny compared with matter on Earth, yet they are real enough to be measured across billions of kilometers. This gives interstellar space a structure that ordinary images cannot show. The plasma data reveals a medium with layers, gradients, and pressure. Voyager is crossing something closer to a faint cloud than a perfect vacuum. The cloud is so thin that a spacecraft can move through it without feeling ordinary resistance. But across the scale of the heliosphere, even this small amount of material becomes important. Our entire planetary system moves through the local interstellar medium as it orbits the center of the Milky Way. The heliosphere travels with it, carrying the planets inside a protective bubble formed by the solar wind. From this perspective, Voyager has moved outside a moving shelter. The spacecraft is no longer only traveling away from the Sun. It is sampling the material flowing around the solar system as both continue through the galaxy. But its particles still have motion, temperature, pressure, and a magnetic relationship with the Sun's outer boundary. It is easy to imagine interstellar space as a neutral gap separating one star from the next. Voyager's measurements show something more complicated. Stars do not sit inside completely empty isolation. They release winds, radiation, and magnetic fields into a larger galactic medium. Each star creates its own local environment, and those environments push against the material between them. The space separating the stars is part of the system, not merely the absence of one. Before Voyager crossed the boundary, many models treated the outer region in relatively simple ways. The solar wind expanded, slowed, and met the surrounding interstellar material. The heliosphere did not behave like a smooth balloon placed inside still air. The spacecraft was never aimed toward the most scientifically useful point on the heliosphere. Its route was chosen to visit Jupiter and Saturn, then continued naturally into the outer darkness. This makes the data both precious and incomplete. A change measured along the path could represent a broad feature extending across the boundary, or it could be something local that exists only near Voyager. Scientists compare the results with Voyager 2, remote observations, and computer models to build a larger picture. Voyager 2 crossed the heliopause in a different direction and carried a functioning plasma instrument, offering measurements that Voyager 1 could not provide directly. The two crossings did not look identical. They occurred at different distances from the Sun and under different solar conditions. This was expected to some degree, because the heliosphere changes over time and is shaped differently in different directions. But the contrast also showed how dangerous it is to imagine one clean universal edge. The solar system does not have a border drawn at the same distance everywhere. The heliopause responds to pressure. A stronger solar wind can push it outward. Changes in the surrounding interstellar medium can press it inward. Large disturbances can temporarily reshape local conditions. The boundary may move while a spacecraft approaches it. Voyager did not cross a fixed wall. It crossed a living frontier created by two enormous environments pressing against each other. The plasma waves preserve part of that interaction. Some signals reveal material compressed by the Sun. Others show conditions belonging more clearly to interstellar space. The persistent background vibration suggests that the local medium remains active even without a strong solar event passing through it. This activity is extremely faint. The converted tones can sound eerie because they are narrow, steady, and unfamiliar. But the unsettling feeling comes partly from knowing where the measurements were made. The signal was collected beyond every planet, in darkness where sunlight is weak and Earth is only a direction for an antenna. The sound is not frightening by itself. Its meaning is, a machine built in the 1970s is detecting the electrical movement of matter outside the Sun's protective bubble. The signal crosses a distance so large that the spacecraft must continue operating for many hours before Earth knows what it measured. By the time researchers listen to the converted data, Voyager has already traveled farther. The environment it recorded lies behind it. This creates a slow delay inside the science. Voyager never reports the exact present conditions around itself. Its radio signal takes more than 20 hours to reach Earth, and the measurements may be processed long after that. Researchers study a region the spacecraft has already left. As Voyager continues outward, every discovery belongs to a slightly earlier position. At human scales, this delay is manageable. At interstellar scales, it is a reminder that distance separates observation from reality, even within our own stellar neighborhood. The plasma signal also gives a new way to think about silence. Silence does not always mean inactivity. Interstellar space is silent to ears, dark to eyes, and almost empty by ordinary standards. Yet charged particles are moving, magnetic fields are present, and waves pass through the medium. Voyager converts part of that hidden activity into measurements. The result resembles a sound, only because sound is one of the ways human minds understand frequency and change. Without the instrument, the plasma would remain invisible. Without the conversion, the data would remain numbers. The familiar tone becomes a bridge between a distant physical process and human perception. It allows people on Earth to experience, in a limited way, the environment beyond the heliopause. But the signal should not be mistaken for a message. There is no evidence that the waves were created intentionally. They do not form language, repeat as an artificial pattern, or point toward another civilization. They are the natural behavior of plasma. The mystery lies not in who created them, but in how much remains unknown about the medium surrounding the solar system. Even nearby interstellar space has been sampled directly in only a few places. Voyager 1 and Voyager 2 provide narrow measurements from two aging machines. Every other conclusion depends on light, particles, and models observed from inside the heliosphere. The region just beyond our solar boundary remains less explored than many planetary surfaces. This makes the faint background signal unusually valuable. As long as Voyager can continue detecting it, scientists can follow changes in density farther from the Sun. The path may reveal whether the plasma becomes smoother, more turbulent, denser, or thinner. It may show how far disturbances from the Sun continue to influence the local medium. It may also help explain whether the spacecraft is moving through a special layer piled up near the heliopause, or entering conditions more typical of the space between nearby stars. Some models suggest that interstellar material can gather outside the heliosphere as the solar system moves through the galaxy. If so, Voyager may be crossing a compressed region rather than a perfectly ordinary sample of the wider interstellar medium. The gradual density changes could reveal the thickness of that region. Farther out, the plasma might settle into a different state. Voyager may lose power before it reaches that point. This is one of the quiet limits hanging over every measurement. The spacecraft is moving into scientifically new territory while its ability to observe is disappearing. Each year, the available electrical power declines. Engineers must choose which instruments remain active and which are turned off, so that the others can survive longer. The plasma wave instrument competes for energy with systems measuring particles, magnetic fields, and the health of the spacecraft itself. A few watts can decide whether humanity continues hearing the interstellar plasma. Eventually, the background signal will end in Earth's receivers. The waves will still exist around Voyager. The plasma will continue vibrating. Only the connection will disappear. The spacecraft will move through the same medium without converting it into knowledge. This future gives the present data a sense of rarity. Voyager is not only far away, it is observing during a limited final period when the machine still has enough power to speak. The plasma waves are one part of that message. But they are not the only sign that the environment changed after the heliopause. As the solar particles faded, another population became much stronger around the spacecraft. These particles carried far greater energies, arrived from the galaxy, and revealed what the Sun's protective bubble had been keeping away from the planets. And once the faint vibration of interstellar plasma had shown that the darkness possessed density, structure, and motion, the rising flood of cosmic rays would reveal how exposed Voyager had become beyond the shelter of the Sun. Voyager continued moving through the same darkness at nearly the same speed. Its antenna remained pointed toward Earth. Its instruments worked with the same declining supply of power, and the Sun still appeared as the brightest point behind it. Inside the heliosphere, the solar wind creates more than a bubble of plasma. It also carries magnetic fields that interfere with many of the high-energy particles arriving from the wider galaxy. These particles are known as galactic cosmic rays. Many are believed to come from violent events, such as supernova explosions. A star can end its life by throwing material outward with enough force to create powerful shock waves. Those shocks can accelerate particles and send them traveling through the Milky Way for thousands or millions of years. Some particles may be shaped by massive stars, stellar remnants, or extreme regions where magnetic fields and matter interact. By the time a cosmic ray reaches Voyager, the event that launched it may be ancient and unimaginably distant. Magnetic fields bend the route of charged particles as they move through the galaxy, so their final direction does not necessarily point toward where they began. Voyager measures their energy and abundance instead. As the spacecraft approached the boundary, particles associated with the Sun began to decrease. At the same time, galactic cosmic rays increased. The heliosphere had been acting as a shield. It does not stop every cosmic ray. High-energy particles still reach Earth and pass through the inner solar system. Some strike the atmosphere and create showers of secondary particles that can be detected at the surface. But the solar wind and the magnetic field carried through it reduce and redirect part of the incoming radiation. When the Sun is more active, its stronger and more disturbed magnetic environment can make it harder for some galactic cosmic rays to reach the inner planets. When solar activity weakens, more can enter. Our planet's magnetic field bends many charged particles, while the atmosphere absorbs and transforms much of the radiation that continues downward. Voyager has neither. Beyond the heliopause, there is no thick atmosphere surrounding the spacecraft, and no planetary magnetic field enclosing it. Its thin metal structure is exposed directly to the particle environment. A cosmic ray can pass through the spacecraft, strike an instrument, disturb electronics, or leave a small path of damage in a material. Voyager was designed to operate in radiation around the giant planets, especially near Jupiter, where trapped particles create an intense environment. Its electronics were built with protection and redundancy. But decades of exposure still matter. Radiation can change bits in computer memory, produce false readings, and slowly damage electronic components. A tiny error can become serious when the spacecraft is too far away for physical repair. Engineers can sometimes correct a problem by sending commands, switching to backup systems, or changing how memory is used. The command may take more than 20 hours to arrive. A response requires the same journey back. The spacecraft must remain stable during the long exchange. They are valuable scientific evidence, revealing what lies beyond the Sun's bubble. They are also part of the environment, slowly aging the machine that measures them. The spacecraft is not observing cosmic rays from beneath an atmosphere or from deep inside the heliosphere. It is sampling them directly in the local interstellar medium. The measurements help scientists understand how strongly the heliosphere changes the radiation environment around the planets. They also reveal how cosmic ray intensity behaves immediately beyond the boundary. Others rose, then changed again. This suggested that the outer edge of the heliosphere contained complicated regions where particles could enter, escape, or move along magnetic field lines. Particles from inside the heliosphere escaped outward. Particles from the galaxy entered more easily. A simple model might predict that solar particles fall, cosmic rays rise, the magnetic field changes direction, and the spacecraft is clearly outside. Voyager did not provide such a neat sequence. Instead, some signs changed before others. The particle environment announced a transition while the magnetic field remained unexpectedly similar. The heliopause behaved less like a door and more like a region whose features overlapped. The spacecraft had entered a harsher radiation environment. Interstellar space is not filled with a bright storm that would be visible through a window. The particles are sparse. A person would not see them approaching. The danger comes from their energy and from exposure over time. A single high-energy nucleus can pass through ordinary material and strike cells deep inside a body. For an astronaut, repeated exposure would increase the risk of cancer, damage tissues, and create effects that are still difficult to predict across very long missions. For electronics, the same environment can create errors and gradual degradation. A crewed spacecraft would be larger, more complex, and expected to protect people for years or decades. Shielding can reduce radiation, but high-energy cosmic rays are difficult to stop completely. Thick layers of water, fuel, or other material can absorb part of the radiation. Yet when an energetic particle strikes shielding, it can break atoms apart and create secondary particles that continue into the spacecraft. Every added layer also increases mass, making acceleration more difficult. For a slow probe like Voyager, mass was already a major concern. For a fast interstellar craft, it becomes one of the central limits. They describe the environment future missions must cross after leaving the heliosphere. The nearest stars are separated from us by several light years of this exposed space. A spacecraft moving at Voyager's speed would remain inside it for tens of thousands of years. A faster probe could reduce that time to decades, but higher speed would create other dangers from dust and gas, while cosmic radiation continued striking it throughout the journey. A mission to Mars remains inside the Sun's bubble. A journey to Jupiter or Saturn moves through regions of intense local radiation, but the spacecraft is still within a system shaped strongly by the solar wind. An interstellar journey must cross the boundary and remain outside. There is no nearby planetary magnetic field waiting to provide continuous shelter. The spacecraft carries whatever protection it will have. The cosmic ray detector counts particles, while the machine slowly loses its ability to respond. Each measurement is a small record of the galaxy passing through the spacecraft. Some particles may have begun their journey before humans existed. Others may have crossed large regions of the Milky Way, guided and scattered by magnetic fields. Before meeting Voyager's sensors, a particle arrives, passes through matter, deposits energy, and continues or disappears inside an interaction. Scientists compare the number of particles, their energies, and how the measurements change over time. It is to understand the population surrounding the solar system. Cosmic ray intensity can change because of events in the heliosphere, changes in the local interstellar medium, or the way magnetic fields guide particles toward and away from the spacecraft. A rise may indicate that shielding from the sun has weakened. A smaller variation may come from a disturbance moving through the plasma. Long-term changes may reveal structure in the interstellar environment. As the spacecraft continues outward, it samples new regions year after year. The region beyond it still responds to the solar cycle and to disturbances traveling outward from the sun. The sun's protection does not end in one perfect step. Its influence fades, leaks, and reaches outward through moving fields and pressure waves. The heliosphere is not only a boundary surrounding the planets, it is a radiation filter shaped by the sun's behavior. Its value is difficult to notice from Earth because we have always lived inside it. Only after a spacecraft leaves can the difference be measured directly. Voyager found that the galaxy beyond contains a larger population of energetic particles waiting outside the solar shield. Our atmosphere and planetary magnetic field provide much stronger protection at the surface. It reduces part of the galactic radiation before that radiation reaches the inner solar system. Some move so close to the speed of light that the heliosphere can only slightly change their path. Voyager's detectors separate parts of this population by energy, allowing researchers to study how the boundary filters different particles. Cosmic rays affect astronauts, satellites, aircraft at high altitude, and even some electronic systems on the ground. They can also create chemical changes in planetary atmospheres and contribute to radiation on worlds without strong protection. It is part of understanding the space environment surrounding human technology. The mission survived long enough for instruments designed for one purpose to answer questions that had barely formed when the spacecraft left Earth. To measure galactic cosmic rays without the full influence of the heliosphere, an instrument must travel beyond the boundary. Their measurements give two small windows into the radiation environment outside. Voyager 2 found its own sharp changes in particle populations during the 2018 crossing. The solar system is currently passing through a region of relatively warm, thin material, often described as the local interstellar cloud. Nearby clouds may have different densities, temperatures, and magnetic properties. Over thousands of years, the heliosphere could change shape as the sun moves into new surroundings. A denser cloud might compress the bubble. A thinner region might allow it to expand. The level of cosmic radiation reaching the planets could change with it. The heliosphere may have grown, contracted, and changed its protective effect many times during the history of life. Still, by measuring the radiation outside the present heliopause, it provides the missing outer value needed to understand how much the solar bubble changes what reaches the planets. Inside the heliosphere, galactic cosmic rays are partly reduced. Outside, their intensity rises. It was recorded directly as Voyager crossed the boundary. Voyager is no longer simply a distant object drifting beyond the planets. It is a machine moving through a constant rain of particles arriving from the Milky Way. But the detectors count it, the electronics endure it, and the slow accumulation becomes part of the spacecraft's final years. Its survival depends on old components tolerating conditions no repair team can reach. The cosmic ray measurements may continue while other instruments are switched off. Eventually, the detector itself may lose power, or the spacecraft may become unable to return useful information. The particle stream will not stop when Voyager does. Cosmic rays will continue crossing the heliopause and moving through the local interstellar medium. The spacecraft will continue being struck long after it becomes silent. Only the record on Earth will end. Before that silence arrives, Voyager is still revealing how the boundary separates two radiation environments. The solar particles that once surrounded it have faded. The galactic particles have become stronger. Between them lies the heliopause, not visible as a surface, but clear in the way energetic matter changes across it. Yet one measurement did not behave as neatly as the particle counts. Scientists expected the magnetic field beyond the boundary to turn toward a noticeably different direction. Instead, the field around Voyager remained surprisingly close to the orientation it had shown inside the heliosphere. The cosmic rays said the spacecraft was outside. The magnetic field made the border look far less certain. And once Voyager had revealed how sharply the sun's protection weakened beyond the heliopause, the magnetic field surrounding the spacecraft became the quieter clue that made the boundary far more difficult to understand. Inside the heliosphere, Voyager was surrounded by the magnetic field carried outward by the solar wind. Beyond the boundary, the spacecraft should have entered a field belonging to the local interstellar medium, shaped by the space between the stars rather than by the sun. But it did not. The strength of the field increased near the heliopause, yet its direction remained surprisingly close to what Voyager had measured inside. The particle instruments said the spacecraft was outside. Solar particles had fallen sharply. Galactic cosmic rays had risen. Plasma density had increased to the level expected in interstellar space. The magnetic field, however, seemed to preserve part of the old pattern. Perhaps Voyager had entered one final outer layer while still remaining inside the heliosphere. Perhaps the true boundary waited farther ahead. Or perhaps the border itself was far less clean than the diagrams suggested. The difficulty came from the way magnetic fields behave in plasma. The solar wind carries the sun's magnetic field outward through the solar system. Because the sun rotates, that field becomes wrapped into a broad spiral stretching far beyond the planets. Outside the heliosphere lies the interstellar magnetic field. As the solar system moves through the local interstellar medium, That external field does not simply stop at the solar boundary. It can bend around the heliosphere, following the shape of the bubble and becoming draped along its surface. If Voyager crossed through a region where the external field had already been bent into a similar direction, then the surrounding plasma could change while the field still appeared familiar. The spacecraft could be outside without seeing the dramatic magnetic turn that scientists had expected. This idea transformed the heliopause from a wall into something more complicated. A magnetic boundary can contain properties of both sides. Particles can escape along certain directions. Cosmic rays can enter along others. The density can change sharply while the field direction changes slowly. Voyager was not passing through a painted line. It was moving through a region where the Sun and the galaxy were pressing against each other. The area just inside the heliopause had already shown unusual behavior. Voyager entered a region where particles from the Sun began escaping more freely, while cosmic rays from the galaxy entered more easily. Researchers sometimes called it a magnetic highway. This helped explain why different measurements changed at different moments. A simple model might predict one clean sequence. Solar particles fall, cosmic rays rise, plasma density changes, and the magnetic field turns. The particle environment looked interstellar, while the field direction still seemed connected to the heliosphere. Only when the denser plasma was measured did the full picture become convincing. The spacecraft had crossed the heliopause, but the boundary did not force every property to change at once. The magnetic field beyond it may also remain affected by pressure from the Sun. Large solar eruptions can send disturbances outward through the heliosphere. These waves may take more than a year to reach the boundary, but they do not necessarily stop there. They can continue into the local interstellar medium. When such a disturbance reaches Voyager, it can compress the plasma and strengthen the magnetic field around the spacecraft. The event began near the Sun, crossed billions of kilometers, passed through the heliopause, and became visible as a change in interstellar space. By the time Voyager detects it, the original eruption belongs to the distant past. The Sunday may have completed many rotations, its activity may have changed, yet the wave still carries part of that earlier moment outward. The spacecraft is beyond the main flow of the solar wind, but it is not beyond every consequence of solar activity. The Sun no longer controls the surrounding matter, yet it can still disturb it. The heliopause is therefore a boundary of dominance, not a perfect seal. Pressure waves, particles, and magnetic effects can still cross between them. The boundary also moves. The strength of the solar wind changes with the Sun's activity cycle. Fast and slow streams collide. Eruptions add temporary pressure. The outer heliosphere responds, but the response takes time because the bubble is enormous. A change near the Sunday may not reach the heliopause for many months. The boundary measured by Voyager reflects a delayed history of solar activity. At the same time, the interstellar medium presses inward. Its density, motion, temperature, and magnetic field all help shape the outer solar system. The heliosphere is created by both sides. It is not simply the Sun expanding into nothing. It is the solar wind holding back a real surrounding environment. The external magnetic field may push more strongly in some directions than others. Its orientation can bend the heliosphere, guide particles around the boundary, and change how pressure is distributed across the surface. This makes the overall shape difficult to determine. Voyager 1 provides only one narrow path through a structure billions of kilometers wide. The spacecraft cannot travel sideways, circle the boundary, or compare several regions at once. Its route was fixed by encounters with Jupiter and Saturn decades before the heliopause crossing. Every new measurement extends the same thin line farther outward. From that line, scientists try to understand the full bubble. The problem is similar to touching one small area of an enormous moving surface and trying to decide whether the whole object is round, stretched, flattened, or divided into lobes. A local curve cannot reveal everything. Remote observations provide broader clues. Instruments closer to Earth can detect energetic neutral atoms created near the edge of the heliosphere. Because these atoms are not electrically charged, they can travel in straighter paths and help form maps of activity across the sky. Those maps have revealed a bright ribbon-like feature linked to the local interstellar magnetic field. The feature shows that the external field influences the heliosphere on a large scale. Voyager measures one point directly. The maps reveal broad patterns from far away. Together they suggest that the solar system's protective bubble is not a simple sphere. For many years, the common image showed a rounded front and a long tail extending behind the moving sun. That shape seemed natural. An object moving through a fluid often creates a compressed region ahead and a wake behind. But the heliosphere is not moving through ordinary air or water. Both sides are plasma. Magnetic fields, matter. Particles exchange charge. The solar wind changes with time. Some models still show a long tail. Others suggest a more compact shape with two broad lobes. The real structure may change as the sun moves through different parts of the local interstellar medium. Voyager 1 alone cannot settle the question. Its crossing occurred in one direction, above the plane where most planets orbit. Voyager 2 later approached the heliopause from another direction, below that plane. The second spacecraft offered a rare comparison. The two crossings happened at different distances from the Sun and during different periods of solar activity. Voyager 1 crossed at about 121 astronomical units. Voyager 2 crossed closer, at roughly 119 astronomical units. The difference may sound small beside the full size of the solar system, but 1 astronomical unit is the distance between Earth and the Sun. A shift of even a few astronomical units represents a vast physical region. Part of the difference may come from the shape of the heliosphere. Part may come from movement of the boundary as solar pressure changed. The crossing distances alone cannot separate those causes. The magnetic measurements add another layer. Voyager 2 found its own complex transition. Its magnetic field increased, the particle populations changed, and its functioning plasma instrument measured the surrounding material more directly. The broad pattern confirmed what Voyager 1 had found. The details were not identical. This mattered because it showed that the heliopause behaves as one kind of boundary without behaving exactly the same everywhere. In some measurements, the crossing appears sharp. Solar particles can fall rapidly. Galactic cosmic rays can rise over a relatively short distance. In other measurements, the transition is broader. Magnetic pressure can build gradually. Field direction can remain similar across the crossing. The heliopause has a clear physical meaning, but different instruments encounter different parts of that meaning. For Voyager, the decisive change was the origin and density of the surrounding plasma. Inside, the plasma belonged mainly to the solar wind. Outside, it belonged to the local interstellar medium. The direction of the magnetic field did not erase that distinction. It revealed that the boundary was shaped by bending, pressure, and connection. This changed the meaning of being outside. Voyager did not leave every trace of the sun behind. Solar eruptions still reached it. The boundary remained shaped by pressure from within. Waves traveled through the surrounding plasma. The spacecraft entered a region where the galaxy had become dominant, but the distant sun still left marks on the environment. The magnetic field is one of the clearest records of that overlap. Its strength reveals compression. Its direction reveals how the external field may be draped around the heliosphere. Its changes reveal passing disturbances. Its structure helps control how charged particles cross the boundary. A field too weak for a human body to sense can influence a region wider than the planetary system. That is possible because the scale is so large. The plasma is thin. The pressure is tiny by earthly standards. The magnetic field is extremely weak compared with an ordinary magnet. Yet across billions of kilometers, these subtle forces determine where the solar wind ends and interstellar space begins. Voyager crossed a frontier that could never be seen through a camera. Only the behavior of invisible matter revealed it. The spacecraft's magnetometer is a quiet instrument. It does not create images or dramatic sounds. It measures the strength and direction of the field around Voyager through sensors placed away from the spacecraft's main body. The readings are small, but their location makes them unique. No modern instrument near Earth can replace a weaker instrument operating beyond the heliopause. The value comes from being there. As Voyager continues outward, scientists can watch for slow changes in the field. If the region near the heliopause contains a bent or compressed layer, the field may gradually turn toward the more undisturbed interstellar direction farther away. That would help reveal how thick the outer disturbed region really is. But the opportunity is limited. Voyager's electrical power decreases each year. The magnetometer may continue operating while other instruments are shut down, but it still depends on the spacecraft remaining stable, warm enough, and able to transmit. The most revealing region may lie ahead after the final signal has already disappeared. Voyager could enter a calmer, more typical part of interstellar space without anyone receiving the measurements. For now, every reading adds one more point to the narrow path extending away from the Sun. Together, those points show that the heliopause is not a clean wall separating two perfectly isolated spaces. It is a changing frontier shaped by solar pressure, interstellar plasma, magnetic fields, and time. Voyager 1 revealed that complexity from one direction. A second spacecraft reached another part of the boundary years later, carrying a different set of working instruments and encountering a different state of the Sun. Its passage offered the closest thing humanity has to repeating the same experiment at the edge of interstellar space. And once Voyager 1's magnetic measurements had shown that leaving the heliosphere was not as clean as crossing a single wall, Voyager 2's passage through a different part of the boundary became the comparison needed to reveal how uneven and changeable that edge truly was. Its journey through the outer planets had taken it past Jupiter and Saturn, then onward to Uranus and Neptune, worlds Voyager 1 never visited. Those encounters sent it away from the broad plane of the planets in another direction, carrying a different collection of working instruments toward a different region of the heliosphere. Voyager 1 moved faster and crossed the heliopause in 2012. Voyager 2 continued through the heliosheath, the wide outer region where the solar wind had slowed, heated, and become compressed before finally meeting interstellar space. By the time Voyager 2 approached the boundary, scientists knew which changes had announced Voyager 1's crossing. They watched for the decline of particles from the Sun, the increase in galactic cosmic rays, the strengthening of the magnetic field, and the arrival of denser interstellar plasma. But they also knew the second crossing might not happen in the same way. The spacecraft was traveling through another part of a boundary that could move with solar activity, bend under interstellar pressure, and behave differently in different directions. During 2018, Voyager 2 began detecting an increase in cosmic rays arriving from outside the heliosphere. The change resembled the pattern Voyager 1 had measured before its own departure from the solar bubble. Cosmic ray levels rise and fall for several reasons. The magnetic environment can change. Solar activity can temporarily alter how particles enter the outer heliosphere. A spacecraft can approach the boundary without having crossed it. Then, in early November, the environment changed sharply. Particles that had originated inside the heliosphere dropped away. Galactic cosmic rays rose to levels similar to those measured by Voyager 1 in interstellar space. The magnetic field became stronger, and several instruments recorded changes consistent with the crossing. The spacecraft was about 119 astronomical units from the Sun, nearly 17 light-hours away at the time. It had been traveling for more than 41 years. the crossing made Voyager 2 the second human-made object to enter interstellar space. But its greatest value was not simply repeating what Voyager 1 had done. Voyager 1's corresponding instrument had stopped working in 1980, long before the first heliopause crossing. Scientists had confirmed Voyager 1's entry into interstellar space, indirectly, by using plasma waves to estimate density. Voyager 2 could measure the plasma flow itself. As the spacecraft approached the heliopause, the instrument detected the solar wind becoming slower and more irregular. Then the outward flow associated with the sun fell away. The plasma surrounding the probe no longer behaved like material streaming outward from the solar atmosphere. This provided a direct measurement of the moment the solar wind ended along Voyager 2's path. The transition happened across a distance that was small compared with the size of the heliosphere, yet still enormous by human standards. Voyager 2 crossed a boundary no eye could see by measuring how invisible matter moved around it. The plasma inside the heliosphere's outer region had been heated as the solar wind slowed and compressed. Beyond the heliopause, Voyager 2 entered interstellar plasma that was denser and cooler than the material immediately inside. Individual particles could still move rapidly, and the gas would be described as warm by astronomical standards. But the comparison helped distinguish the two environments clearly. The difference confirmed that the heliopause was not only a change in particle intensity, it separated plasmas with different origins, densities, temperatures, and patterns of motion. Voyager 2 detected a thin layer near the heliopause, where material from the heliosphere appeared to leak outward. At the same time, some interstellar particles could enter inward. The boundary held back most of the solar wind, but it did not isolate the two regions completely. The heliopause is a surface where pressure reaches a balance, not a solid membrane. Charged particles respond to magnetic fields, and some can move along paths that cross the boundary. Neutral atoms can pass through more easily because they are not guided in the same way by magnetism. Changes in several particle populations occurred over a relatively short distance. The solar wind disappeared quickly, while galactic cosmic rays became more common. The magnetic field strengthened, but its direction remained surprisingly similar on both sides, confirming the puzzle first seen by Voyager 1. Both found that the external magnetic field near the boundary was merely parallel to the field inside. The similarity suggested that the interstellar field was being shaped around the heliosphere. It may be draped along the outer surface, compressed and bent by the motion of the solar bubble through the surrounding medium. Voyager 1 reached interstellar space at roughly 121 astronomical units from the Sun. Voyager 2 crossed at about 119. The heliopause was therefore closer along Voyager 2's route, at least at the time of its passage. Voyager 1 and Voyager 2 were moving through different parts of the heliosphere. They also crossed 6 years apart, after changes in the Sun had traveled outward and altered conditions near the boundary. Solar activity follows an approximate 11-year cycle, but the outer heliosphere responds slowly. Variations in solar wind pressure need months or years to travel beyond the planets. The distant boundary can therefore expand or contract in response to a version of the Sun's activity that is already old by the time the change arrives. The location it measured was not an eternal border marked permanently in space. It was the position where solar and interstellar pressure balanced on one date, along one direction, during one stage of the solar cycle. This movement helps explain why predicting the crossing had been difficult. Before the event, scientists could estimate Voyager 2's distance from the boundary, but they could not know precisely whether the heliopause was drifting inward or outward. A strong region of solar wind could push the boundary farther outward. A period of lower pressure could allow interstellar material to compress it inward. The two Voyagers provided only 2 points, but those points were enough to expose the weakness of a perfectly round model. If the heliosphere were a stable sphere, Both crossings would have occurred at distances determined only by their directions through that sphere. Instead, the observations had to include magnetic distortion, changing solar pressure, the flow of interstellar material, and the possibility that the boundary moved substantially over time. Voyager 2 added another physical measurement to a structure still too large to observe directly from outside. Researchers must combine local spacecraft data with remote maps, particle detections, magnetic measurements, and computer models. The Voyagers are like two tiny weather stations, placed on opposite portions of an invisible planetary atmosphere. Except the atmosphere is larger than every planetary orbit, and the stations can never be moved. The information they return becomes more valuable because no third spacecraft is close to repeating the experiment. New Horizons is traveling through the outer solar system, but it remains far inside the heliopause and moves more slowly than Voyager 1. Voyager 2's plasma instrument made its crossing especially valuable. But even that instrument could not continue forever. Its measurements became limited after the spacecraft entered interstellar space because of the direction in which the plasma flowed relative to the instrument. The spacecraft's orientation had been chosen mainly to keep its antenna pointed toward Earth, not to place every detector in the perfect position for the new environment. A mission designed specifically for interstellar space would arrange its sensors differently. Voyager 2 was using hardware created for planetary exploration to study a region no spacecraft had reached when the design was completed. Its instruments observed the magnetospheres of giant planets, the solar wind across billions of kilometers, the slowed plasma of the heliosheath, and finally, the interstellar medium. The fact that the plasma experiment survived long enough to identify the heliopause was partly the result of careful engineering and partly the result of extraordinary longevity. After the crossing, its direct measurements confirmed that the plasma outside was denser than the material within the solar bubble. They also showed a density gradient farther from the heliopause, suggesting that the interstellar medium near the boundary was not perfectly uniform. The solar system moves through the local interstellar cloud, and the bubble around the Sun pushes into that surrounding plasma. Just as water can gather and change flow around an object, interstellar matter may form altered layers near the heliopause. Although the physics is controlled by plasma and magnetic fields, rather than ordinary fluid alone, the measurements did not necessarily represent untouched interstellar space, far from every star's influence. They represented the local medium after it had interacted with the heliosphere. Together, the results suggested that both spacecraft were moving through a region shaped by the presence of the solar bubble, even after crossing outside it. The Voyagers are in interstellar space because the plasma around them no longer comes mainly from the solar wind, but they remain near the heliosphere compared with the distance between stars. Voyager 2's crossing made this layered geography easier to understand. Outside lies the local interstellar medium, itself altered near the boundary by pressure and magnetism. They are defined by changes in particles and fields. A probe can cross them while the darkness looks unchanged. Its long path showed that the outer solar system is not simply emptier and colder with distance. The physical environment changes character. The comparison between the two spacecraft also offered a way to test which discoveries were local and which belonged to the heliopause more generally. Both detected sharp declines in heliospheric particles. Both found increases in galactic cosmic rays. Both entered denser interstellar plasma. Both measured magnetic fields that stayed unexpectedly aligned across the boundary. These shared features became stronger evidence because they appeared in separate places and at separate times. Voyager 2's direct plasma flow measurements added information that Voyager 1 could not provide. It could be sharp without being solid, open to some particles while stopping the solar wind, magnetically connected, while separating two different plasmas. The Voyagers crossed that balance at two locations and continued outward, leaving scientists to reconstruct the full surface from narrow trails of data. Their continued motion may reveal how far the disturbed region extends beyond the heliopause. If density, temperature, or magnetic direction gradually change, those changes can show where the influence of the boundary begins to fade. Voyager 2's plasma science instrument, the tool that gave the most direct evidence of the 2018 crossing, was eventually switched off as part of the effort to conserve power. The boundary it had discovered remained around the distant sun, but the instrument could no longer continue following the plasma farther outward. Not with one sudden shutdown, but through a sequence of quiet losses. The spacecraft continues, while its ability to describe the environment gradually disappears. Most importantly, it showed that the edge itself records events happening far inside the solar system. Changes in solar pressure travel outward for years before reaching the heliopause. When they arrive, they can move the boundary, compress the interstellar plasma, and send disturbances beyond the region where the solar wind has ended. The sun continues affecting the darkness outside its own bubble through delayed waves that Voyager can detect long after the original eruption has disappeared from view. And once the two Voyager crossings had revealed a heliopause that changed with direction, pressure, and time, the solar storm still traveling beyond that boundary became the clearest evidence that leaving the heliosphere did not mean leaving the sun's distant reach behind. Magnetic fields near the sun twist, break, and reconnect. Energy stored across enormous regions can be released in a short time, heating plasma and throwing charged particles outward. It crosses the orbit of Mars, passes Jupiter, moves beyond Saturn, and enters regions where sunlight has become weak. The original eruption may fade from human attention, but the pressure wave it created keeps traveling through the heliosphere. The sun that produced the event has changed. New regions have formed on its surface. Other eruptions have followed. The storm itself has expanded, mixed with the solar wind, and become part of a much larger moving structure. The spacecraft does not see the original flare. It measures a delayed arrival through changes in particles, magnetic fields, and plasma waves. A disturbance born near the sun can compress the material around Voyager even after the probe has crossed into interstellar space. This is possible because the heliopause is not a solid barrier. The solar wind ends there as the dominant outward flow, but pressure waves can continue through the boundary and enter the local interstellar medium. When they do, the plasma outside the heliosphere is pushed together. Electrons begin oscillating more clearly, allowing Voyager's plasma wave instrument to detect the response. The spacecraft becomes a listener, waiting for impacts that began far behind it. These events are sometimes connected to enormous merged structures in the solar wind. A single eruption expands as it moves outward. Several eruptions launched at different times can catch one another, combine, and form a broader wall of disturbed plasma. By the time such a structure reaches the outer solar system, it may no longer resemble one isolated storm. It can become a large region of compressed particles and magnetic fields moving through the heliosphere. Far beyond the planets, the same event can spread across a region large enough to take Voyager weeks or months to pass through. Several storms may blend so completely that scientists must reconstruct their history from measurements taken near the sun and signals detected years later in the darkness. The journey outward changes the disturbance. It becomes less like one explosion and more like weather moving through an invisible ocean. It records a rise in magnetic field strength, a change in energetic particles, or a burst of plasma oscillations. Scientists on Earth compare the timing with solar activity from the past. They calculate how quickly the disturbance may have traveled and how it changed on the way outward. The process is uncertain because the solar wind between Earth and Voyager is not measured everywhere at once. A storm may interact with earlier material long before it reaches the heliopause. The final structure detected by Voyager can be the result of several events whose separate identities were lost during the journey. This makes the spacecraft a kind of distant weather station. It is measuring the outer response of the entire heliosphere. The pressure wave tells scientists how energy moves from the Sun into regions beyond every known planet. It shows that solar activity can influence interstellar plasma across a distance of billions of kilometers. The effect is not immediate. A powerful solar wind disturbance takes much longer because its particles move far below the speed of light. The delay creates a layered picture of time. By the time scientists receive the data, they are studying the final echo of an event that may be several years old. The Sun is being observed at two different times. Voyager reveals what earlier activity has finally become after crossing the full width of the heliosphere. This delayed record is useful because the outer solar system cannot be understood from the current appearance of the Sun alone. Conditions near the heliopause are shaped by solar behavior from the past. A period of strong solar wind can push pressure outward and alter the position of the heliopause years later. A quieter period may allow interstellar pressure to press the boundary inward. Voyager can encounter a frontier shaped by a version of the Sun that no longer exists. The field carried through. The solar wind preserves the changing pattern of solar rotation and activity as it moves outward. Far from the Sun, different regions of solar wind can fold together and become compressed. The outer heliosphere stores a stretched history of the star. Solar storms crossing the heliopause make this history visible outside the bubble. The interstellar plasma responds even though it did not originate at the Sun. A passing wave can push electrons into stronger oscillations and create the frequencies used to measure local density. Some of Voyager 1's clearest plasma detections occurred because solar disturbances made the surrounding medium easier to hear. Without those events, the interstellar plasma could remain too quiet for the same kind of measurement. The Sun therefore helps illuminate the environment beyond its own boundary. This interaction revealed that the heliopause is not only the place where the solar wind stops, it is also a surface capable of transmitting disturbances from one side to the other. The details depend on magnetic fields, particle density, and the angle at which the disturbance meets the boundary. Voyager 2 provides another path, but even two measurements leave most of the surface unseen. A storm may cross the heliopause differently in another region. The same solar event could produce several different responses across the outer solar system. This unevenness makes the heliosphere behave less like one object and more like a changing environment. Its front may be compressed by the motion of the Sun through interstellar space. Magnetic pressure can shake the bubble in directions unrelated to the planets. Solar storms move through this structure and reveal parts of it by the way the boundary responds. A sufficiently strong disturbance may push the heliopause outward temporarily. Later, when the pressure weakens, the boundary can move back. Voyager may cross regions affected by these motions without knowing whether the spacecraft moved through a fixed feature or whether the feature moved across the spacecraft. If the boundary itself shifts, a probe near the heliopause could move between solar and interstellar conditions more than once. A temporary increase in solar pressure could surround a region that had previously appeared interstellar. The heliopause does not usually sweep back and forth across the Voyagers on short timescales, but the possibility shows why the outer edge must be treated as dynamic. Voyager is close enough to measure this struggle directly. It has crossed the heliopause, but it has not traveled far into the space between stars. This means the disturbances it detects beyond the heliopause are happening in the region immediately surrounding the solar bubble. Eventually, the interstellar medium should become less affected by individual solar events. Voyager may not remain active long enough to reach that calmer region. Its measurements could end while the spacecraft is still traveling through interstellar space, disturbed by the nearby heliosphere. If that happens, humanity's first direct record beyond the solar boundary will remain a record of the transition zone rather than of completely undisturbed space between the stars. This is another reason the Voyager discoveries must be interpreted carefully. The surrounding plasma belongs to the galaxy, yet it has been compressed and shaped by the heliosphere. The magnetic field is interstellar, yet it may be draped around the solar bubble. The cosmic rays are galactic, yet their intensity can still respond to conditions near the boundary. The solar storms are born at the sun, yet they can continue into the plasma outside. Solar disturbances also provide information about the material they cross. A wave moving through denser plasma behaves differently from one moving through thinner plasma. Its speed, strength, and ability to create oscillations depend on local conditions. By comparing the timing of a solar eruption with Voyager's later detection, researchers can estimate how the disturbance traveled through the outer heliosphere. The event becomes a natural experiment performed across billions of kilometers. These measurements can improve models of the heliosheath, the heliopause, and the interstellar medium just beyond it. A spacecraft leaving the heliosphere will not enter a perfectly calm region. It may encounter disturbances that began at the Sun years earlier. Sensitive instruments could experience changing radiation and magnetic conditions even after crossing the boundary. The storms Voyager detects are weak compared with the direct conditions near the Sun, but distance does not erase them completely. The outer environment carries memory. A violent event can leave the Sun, change shape beyond recognition, and still affect plasma in interstellar space long after the light from the original eruption has passed Earth. This separation between light and matter means scientists can observe the same event in several forms across several years. Its eventual contact with Voyager becomes the last stage of the event's physical journey through the solar system. Yet, Voyager's data does not return instantly. The spacecraft must describe the disturbance using a transmitter whose power is weaker than many household light bulbs. By the time it reaches the antennas of the deep space network, it is extraordinarily faint. The information may describe a large pressure wave, but it arrives as a whisper. Voyager detects structures stretching across millions or billions of kilometers, then reports them through a narrow stream of radio data. Engineers must listen with enormous antennas and carefully separate the spacecraft's transmission from natural background noise. The solar storm may have crossed the heliopause with enough pressure to shake interstellar plasma. Its report reaches Earth as energy so weak that receiving it becomes an act of precision. A measurement that cannot be transmitted is lost. The instruments may function perfectly, but without power for the radio system and accurate pointing toward Earth, the result remains trapped inside a machine, moving away forever. This is why the spacecraft must keep its large dish aligned with a planet it can no longer see as more than a direction. Small thruster firings adjust the orientation. Commands from Earth correct errors. The probe carries out each instruction many hours after it was sent. Every successful exchange proves that the connection still exists across the darkness. The solar disturbances reveal the sun's fading physical reach. The radio signal reveals a different reach moving in the opposite direction. One travels outward from the star as plasma and pressure. The other travels inward from Voyager as electromagnetic waves carrying information. They cross the same distance at very different speeds. A solar storm may need years to reach the spacecraft. Voyager's radio signal returns in less than a day because it travels at the speed of light. Even so, the communication delay is now long enough that no conversation can happen in real time. A command is sent. Earth waits. Voyager receives it many hours later, acts, and sends a response. Earth waits again. One simple exchange can take nearly 2 days. The machine is still within the Sun's gravitational system, and still close on the scale of the galaxy, yet ordinary communication has already become a slow sequence of messages. This delay will continue increasing until Voyager falls silent. Before that moment, every report from beyond the heliopause must cross a gap larger than any earlier mission had maintained. The faint signal carries the plasma waves, cosmic rays, magnetic measurements, and evidence of solar storms reaching interstellar space. Without it, the discoveries would exist only inside the spacecraft. And once the sun's delayed storms had shown that physical disturbances could still reach Voyager beyond the heliopause, the far weaker radio signal, traveling back toward Earth, became the fragile thread carrying every discovery home across the darkness. Voyager's dish is not large by the standards of a ground observatory, yet it must send information across a distance measured in tens of billions of kilometers. The transmitter has only a small amount of electrical power available, and the radio beam spreads as it travels. What remains is weaker than the ordinary background noise surrounding the antennas that receive it. NASA's Deep Space Network listens through enormous radio dishes placed in different parts of the world. Their locations allow Earth's rotation to carry the connection from one station to another, while Voyager remains far beyond the horizon of any single site. A message that would vanish inside an ordinary receiver can slowly emerge through careful processing. Measurements from the instruments are converted into numbers, stored, arranged, and sent through the radio system at a very low data rate. The transmission may contain information about plasma waves, cosmic rays, magnetic fields, temperatures, voltages, or the condition of the spacecraft itself. Each number represents something that happened many hours earlier around a machine moving farther away while Earth listens. The delay is unavoidable. Radio waves travel at the speed of light, but even light requires more than 20 hours to cross the distance between Voyager 1 and Earth. A command sent from Earth cannot produce an immediate response. Mission controllers transmit the instruction and wait for it to arrive. Voyager receives it many hours later, checks the command, and begins the requested action. If the spacecraft sends confirmation, the reply requires the same long journey home. Nearly 2 days can pass before engineers know whether one instruction worked. Voyager must survive during the silence between messages. Its onboard systems carry out stored instructions, monitor basic conditions, and enter protective modes when certain limits are crossed. There is no person guiding each movement in real time. The spacecraft was designed to function at a distance where help would always arrive late. A command that is correct when transmitted may reach a spacecraft whose condition has changed during the delay. Engineers must understand not only what Voyager reported, but what is likely happening by the time the instruction arrives. The conversation between Earth and Voyager is therefore never taking place in one shared moment. It is still close compared with the distance to Proxima Centauri, yet the delay is already long enough to remove immediate control. The radio beam must also be aimed with extraordinary precision. Voyager's dish remains pointed toward Earth, but Earth is not a visible world from that distance. It is part of a tiny inner region around the Sun. Voyager uses small thrusters to control its attitude and keep the antenna aligned. They have operated in extreme cold for decades, using limited fuel and hardware that cannot be repaired. Engineers have revived backup thrusters that had not been used for many years. The same machine that once passed close to Jupiter now uses its remaining fuel mainly to keep one narrow radio connection alive. The frequency of the transmitted signal changes slightly because Voyager and Earth are moving relative to each other. The motion produces a Doppler shift, moving the signal away from the exact frequency at which it was sent. Receivers predict this change and follow the carrier as it drifts. By measuring it precisely, navigators can estimate the spacecraft's speed and motion along the line of sight. The round-trip delay helps refine the position of a spacecraft that cannot be seen as an ordinary object. Even after decades, its path can be measured through the behavior of the radio link. Voyager's transmissions are slow, but they require long listening sessions and some of the network's most sensitive equipment. As the signal weakens, larger antennas or combinations of several dishes become more important. A modern observatory can produce more information in minutes than Voyager transmits over long periods. But no modern observatory is beyond the heliopause. A few bits arriving from that position can answer questions that much larger instruments near Earth cannot reach directly. During the flybys, Voyager sent images and measurements while large objects filled its cameras and mission teams prepared for rapid streams of information. The remaining instruments produce much smaller amounts of data. The radio system sends them slowly, using coding that allows weak transmissions to be reconstructed even when parts are damaged by noise. If some bits arrive incorrectly, computers can use the surrounding structure to recover the intended information. What reaches Earth may be incomplete at first, but processing can rebuild a usable record. Behind each result is a transmission that spread across billions of kilometers and reached Earth at the edge of detectability. The Deep Space Network must listen at the right time. The uplink signal sent from the ground is far more powerful than Voyager's reply, but it faces the same spreading across distance. The probe's receiver must recognize the command and distinguish it from noise. The onboard computer must interpret an instruction written for hardware designed in the 1970s. Modern engineers cannot simply upload large new software systems in the way a phone or computer receives an update. Changes must be small, carefully tested, and compatible with systems whose behavior has been shaped by nearly half a century in space. The wrong instruction could switch off a needed system, change the antenna orientation, or place the spacecraft in a condition from which recovery is difficult. Testing on Earth uses models and old documentation, but no ground copy has aged in exactly the same way as Voyager. Engineers must work with a machine that is partly understood through records and partly understood through what it still reports. Engineers had to determine whether the problem came from memory, a computer subsystem, the formatting of telemetry, or another part of the communication chain. The recovery of useful data from an old spacecraft can take months. It is because every test happens across a distance that turns ordinary troubleshooting into a slow conversation. A solution must preserve the remaining mission, rather than only solve one symptom. It is the only path through which Voyager can be examined, guided, and repaired. Engineers cannot touch the spacecraft, but telemetry allows them to infer what is happening inside it. The spacecraft describes itself through the same faint stream that carries news of interstellar space. The spacecraft must spend power gathering measurements, processing them, keeping itself warm, controlling its orientation, and communicating. Every watt used in one place is unavailable somewhere else. As power falls, the amount of science and the ability to protect the spacecraft both become harder to preserve. Communication itself requires energy. The transmitter must remain strong enough for Earth to detect. The antenna must stay correctly pointed. The computer must continue producing a readable signal. A spacecraft can survive physically while becoming unreachable. It might continue moving, its instruments perhaps still capable of sensing the environment, while Earth receives nothing. From the ground, the difference between a silent but functioning probe and a dead probe could become impossible to determine. Silence removes the only evidence. This possibility gives every faint carrier signal unusual importance. Sometimes the carrier can be detected even when telemetry cannot be decoded. That narrow tone shows that the transmitter is operating, and the antenna still points close enough to Earth. It is the smallest possible sign of life from a spacecraft. No scientific measurement may be present. No detailed health report may be readable. But the tone confirms that a machine beyond the heliopause still exists as an active source, rather than only a remembered trajectory. The signal also carries the history of the mission through time. A transmission received today began many hours earlier. While it was traveling, Earth rotated, people changed shifts, weather moved across the antenna sites, and Voyager continued several 100,000 kilometers farther along its path. The data arrives from a place the spacecraft has already left. This was also true during the planetary encounters, but the delay was measured in minutes or a few hours rather than nearly a day. At the present distance, every message is already part of the past before anyone can read it. The effect is quiet, but profound. Voyager is the most distant active connection humanity has maintained. The machine is not simply far away in space. It is separated from Earth by a growing interval of time. Control, observation, and response are stretched across that interval. The mission exists through patience. An antenna listens for hours. A command travels outward. A team waits. A carrier tone returns. A few lines of telemetry appear. The process may seem slow compared with the dramatic planetary flybys, yet it is exactly this slow exchange that allows the interstellar mission to continue. Without the communication system, Voyager would have become only a silent object soon after Neptune and Saturn were left behind. Its later discoveries depended on the decision to keep listening. They also depended on infrastructure, on Earth surviving across generations. Antennas were upgraded. Receivers became more sensitive. Data processing improved. Mission teams changed while knowledge had to be passed forward. The spacecraft remained largely the same, but Earth learned how to hear it more carefully. This is an often overlooked part of deep space exploration. The lifetime of a mission is not determined only by the hardware that leaves Earth. It also depends on whether people, budgets, antennas, software, and technical knowledge remain available decades later. A working spacecraft can become scientifically useless if no one maintains the systems needed to communicate with it. Voyager's continued voice exists because the connection has been preserved at both ends. The probe protects its aim toward Earth. Earth continues building the ability to detect the probe. Between them lies only space and the rules of radio transmission. There is no relay station near Pluto. No satellite waits at the heliopause. No device strengthens the signal halfway home. The message crosses the entire distance alone. This is what future interstellar communication will also require, only on a much greater scale. A probe near another star would transmit across light years. Its message could take years to arrive and be far weaker than Voyager's. The spacecraft would need greater power, a more focused beam, or receiving systems far larger than those used today. It might send data for months or years before Earth collected enough energy to reconstruct a complete image. Voyager is not testing that full distance, but it is showing the basic difficulty. Every increase in range weakens the signal and lengthens the delay. The farther a machine travels, the more independent it must become, and the harder its discoveries are to return. For now, Voyager remains within reach. The contact is faint, delayed, and dependent on equipment operating with little margin, but it still works. The radio beam carries evidence that plasma vibrates between the stars, that cosmic rays rise beyond the heliosphere, that magnetic fields bend around the solar boundary, and that storms from the sun can continue into interstellar space. All of those discoveries arrive through a transmitter using only a small amount of power from a source that has been weakening since launch. The radio system cannot be separated from that decline. As the spacecraft's generators produce less electricity each year, engineers must choose which heaters, instruments, computers, and communication systems will continue receiving power. The signal may still be detectable, but only if the aging machine can keep generating it. And once the radio link had revealed how much precision was required to carry a whisper from interstellar space back to Earth, the shrinking power supply inside Voyager became the deeper limit, deciding how long that whisper could continue. Far beyond the orbit of Jupiter, sunlight is too weak for the small solar panels available in the 1970s to support a mission lasting decades. The spacecraft instead carries 3 radioisotope thermoelectric generators, devices that turn heat from radioactive decay into electricity. The material releases heat naturally as its atoms decay. There is no flame, no moving turbine, and no reactor controlling a chain reaction. The heat simply continues, slowly and predictably, while thermoelectric materials convert a small part of it into electrical power. They could operate far from the sun, survive without maintenance, and provide steady power through the planetary encounters. But steady does not mean permanent. The plutonium gradually produces less heat. The thermoelectric materials also become less efficient after decades of radiation and extreme temperature changes. Year by year, the amount of usable electricity falls. Instead, the mission loses a few watts, then a few more, until systems that once operated together can no longer all remain active at the same time. The spacecraft still moves correctly through space. Its antenna can still point toward Earth. Several instruments may still be capable of measuring the environment. Every instrument, heater, computer, receiver, transmitter, and control system draws from the same shrinking supply. They cannot add a battery, repair a wire, or install a more efficient computer. They can only decide how the remaining power is used. A heater may be switched off because an instrument appears able to survive at a lower temperature than expected. A scientific sensor may be disabled so that the communication system can continue. A backup device may remain unpowered until the primary system fails. The spacecraft becomes a careful balance in which saving one function can shorten another. Electronic components do not simply need power to operate. Many also need heat to remain within safe limits. A heater that seems unnecessary may be protecting a fuel line, an instrument, or a computer component whose true limit was never tested for half a century. Turning it off can save electricity immediately while creating a new risk later. Equipment designed for one temperature continues working below it. Thruster lines remain usable. Instruments return data after heaters have been removed from their circuits. Voyager's engineers know the original design, the test results, and decades of telemetry. They do not know every detail of how each material has aged in interstellar space. The shrinking power supply forces the spacecraft closer to these unknown limits. Cameras photographed clouds, rings, moons, and magnetic environments. Scan platforms moved. Heaters protected equipment prepared for brief encounters. The cameras were switched off. Other instruments ended their work as the mission changed from planetary exploration to the study of the outer heliosphere. That transformation allowed Voyager to continue for decades beyond its original purpose. The planetary observatory became a particle and field laboratory. Later, even that laboratory began losing instruments. Heaters were removed so the transmitter could remain strong enough to reach Earth. The spacecraft was gradually reduced to the few functions that still had unique value. If the electrical load changes suddenly, the distribution system must remain stable. A command that activates one device may require another to be switched off first. It may switch to backup hardware, change how power is distributed, or attempt actions created for circumstances expected during the original mission. A response that protected Voyager in the 1980s may place new stress on components that have aged for decades. Temperatures, currents, and voltages reveal how the spacecraft is changing. The information arrives many hours late, but it is still the only way to see inside the machine. There are only symptoms, records, careful reductions, and attempts to keep the most important systems alive. Their decay follows physics rather than mission schedules. This gives engineers a predictable decline, but no way to pause it. The mission is rewarded for survival by receiving less energy with which to survive again. A spare circuit may still work, but switching to it can require more power. An unused heater may protect a component, but keeping it active can force the shutdown of an instrument. A redundant computer may provide safety, yet the spacecraft may no longer have enough margin to operate certain combinations comfortably. Engineers examine circuits designed decades earlier and ask whether every load is still necessary. Turning off a few watts can extend scientific operations, but each decision must be tested through models and reasoning, rather than through direct inspection. The new temperature or voltage may take time to settle. A power-saving change can require days before its consequences are understood. Its systems depend on one another. The carrier signal might remain detectable after detailed data becomes unreadable. At some point, Earth may hear only a narrow tone. Then even that tone may disappear. The spacecraft will not know that the mission has ended. Its generators will continue releasing heat. Some circuits may remain active for a time. The antenna may still point near the sun, but without enough power to create a detectable signal, Voyager will become silent. Silence may arrive because the transmitter stops. It may arrive because attitude control can no longer keep the dish aligned. It may arrive because the command system fails, the receiver loses sensitivity, or the power distribution becomes unstable. The final cause may never be known with certainty. A last message could appear normal. The following contact could fail. Engineers might listen again, change antennas, search nearby frequencies, and send commands. For a time, uncertainty would remain. The spacecraft might be alive but misaligned. It might be transmitting too weakly. It might have entered a protective state, or it might have suffered a permanent failure. Distance makes those possibilities difficult to separate. The end of communication would not stop the journey. Voyager would continue along the path shaped by gravity assists around the giant planets. No engine is needed to keep it moving through interstellar space. The probe has enough speed to escape the sun, and there is almost nothing to slow it down. Its electrical death and its physical motion are unrelated. The machine can travel for millions of years after its last watt becomes useful. This creates a strange difference between the mission and the object. The mission depends on power, communication, people, and interpretation. The object depends only on momentum. One will end soon on cosmic timescales. The other may outlast civilizations, continents, and perhaps the familiar arrangement of stars in the sky. For now, engineers remain between those two futures. They work with the spacecraft as an active machine, trying to delay the moment when it becomes only an object. The work is not dramatic from day to day. It involves reviewing telemetry, preparing commands, checking old records, and deciding whether one more heater or instrument can be sacrificed. A few watts become years. A small adjustment can preserve a scientific channel that continues measuring a region no replacement spacecraft can reach. The value of each watt has grown because the location is unique. Near Earth, electricity is cheap, and instruments can be repaired or replaced. Beyond the heliopause, 1 watt can determine whether humanity continues receiving direct evidence from interstellar space. The generators were never expected to become symbols of endurance. They were practical devices, chosen because sunlight would fail in the outer solar system. Their slow decay now sets the rhythm of the mission. Plutonium atoms release heat. Thermocouples convert part of it. Old wiring carries the current. Computers distribute it. Engineers decide what receives it. The entire interstellar mission rests on this quiet chain. The power loss also affects how often Voyager can correct its orientation. Thruster firings require valves, heaters, sensors, and computer control. If fuel lines become too cold, the spacecraft may lose the ability to point its dish accurately. If attitude control becomes unreliable, the radio link can disappear even while the transmitter still works. The spacecraft must spend energy to keep communicating, and it must communicate so engineers can manage its energy. The two problems tighten around each other. Aging thrusters add another uncertainty. The small jets have fired countless times over decades. Their performance can change as parts wear and fuel behaves differently at low temperatures. Engineers may lengthen or shorten pulses to maintain the same movement. Backup thrusters can be used, but they have their own histories and limits. The power system cannot solve mechanical aging, yet it determines which heaters and controls remain available to manage it. Computers create similar concerns. Voyager's electronics were built with technology far less powerful than modern consumer devices. But raw speed is not the main issue. The systems were designed for reliability, radiation resistance, and predictable operation. They have survived because their tasks are narrow and carefully controlled. Still, memory can fail. Timing can drift. A circuit can become unstable after decades of exposure. When that happens, engineers must find a solution that fits inside the available power, memory, and communication limits. The shrinking electrical budget makes every repair more difficult. A workaround may require another subsystem to stay active. A different data path may use more power. An extra heater may protect a failing component but shorten the life of a scientific instrument. There is rarely a perfect choice. The goal is to preserve the greatest remaining value without creating a new danger. That value changes with time. At one stage, plasma measurements may be the priority. At another, magnetic fields or cosmic rays may offer the best science. Later, maintaining contact and understanding the spacecraft's final condition may become more important than operating every sensor. The mission is continuously redesigned without changing the hardware. Only the use of the hardware changes. This is one of Voyager's deepest engineering achievements. The spacecraft survived not because it remained untouched, but because generations of teams learned how to remove functions, revive backups, change procedures, and operate closer to limits that no original plan expected to reach. Its longevity is partly built into the machine and partly created on Earth. The power supply links those two forms of survival. The generators provide the remaining physical energy. Human knowledge decides how that energy becomes time. Every shutdown is both a loss and an extension. Every saved watt closes one window while keeping another open. The final configuration will be the smallest version of Voyager that can still speak. It may carry only a few active sensors and the systems needed to point and transmit. The spacecraft that once returned detailed images of entire worlds will become a faint radio source reporting invisible fields and particles from the darkness. That reduction does not make the mission less remarkable. It reveals what was always most essential. A detector observes. A computer remembers. An antenna points home. A generator supplies just enough power for the message to leave. Everything else has gradually fallen away. The remaining systems have lasted so long that their behavior can no longer be understood only from original expectations. Engineers depend on old diagrams, archived commands, past anomalies, and the spacecraft's own telemetry to learn what it can still tolerate. Each successful recovery adds new knowledge about a machine no one can examine directly. And once the fading generators had reduced Voyager to a careful balance of heaters, instruments, computers, and radio power, the survival of its aging electronics became the final engineering struggle between a spacecraft designed in the 1970s and the interstellar darkness surrounding it. They were built for a different age of spaceflight, when memory was measured in tiny amounts, processors worked slowly, and every instruction had to be written for a machine with almost no room for waste. They had to receive commands from Earth, control instruments, point the spacecraft, collect measurements, prepare telemetry, and react when something went wrong. They had to do this near giant planets, through intense radiation, and later in a place no spacecraft had entered before. It comes from simplicity, careful design, backup systems, and decades of patient work from engineers on Earth. Radiation can damage memory. Electrical components can drift away from their original behavior. Connections can weaken. A circuit that worked normally for 40 years may begin producing errors without warning. It can only reveal symptoms through telemetry, and even that depends on the failing systems remaining capable of describing themselves. In late 2023, Voyager 1 continued sending a radio signal, but the information inside it became unreadable. The carrier tone showed that the spacecraft was still alive. It was receiving commands and maintaining its orientation. Yet the stream that should have contained science and engineering data repeated patterns that made no useful sense. The spacecraft might have been functioning normally, except for the way data was being prepared. It might also have been experiencing a deeper problem that engineers could no longer see because the health reports themselves had become corrupted. The problem was traced to the flight data subsystem. This computer gathers information from the scientific instruments and engineering systems, packages it into a usable form, and passes it toward the radio transmitter. Without it, Voyager can still send a signal, but the signal cannot explain what the spacecraft has measured or how well it is surviving. Engineers suspected that part of the subsystem's memory had failed. A single damaged chip contained a portion of the software code needed to organize the data. The chip could not be repaired, and there was no spare memory area large enough to hold all the missing code in one place. The only solution was to redesign the way the old computer used the memory that still worked. Engineers divided the affected code into smaller sections and placed those sections in different available locations. Every reference pointing toward the old memory addresses also had to be changed so that the separated pieces would still operate as one program. Documentation had to be studied carefully. Old records were compared. Every change had to fit inside the remaining memory without damaging another function. Then, the instructions had to be sent across more than 20 hours of light travel. The command reached Voyager long after it left Earth. The spacecraft attempted the change alone. Its response then began the same long journey back. The first useful engineering data returned after months of unreadable transmissions. Later, changes restored the return of science data as well. The most distant active spacecraft had been repaired without anyone touching it, using a rearrangement of code inside a computer built before modern personal computers became common. The new arrangement used memory that had originally been intended for other purposes. The spacecraft continued with less flexibility and one more layer of dependence on a workaround. A damaged path is avoided. A backup system is revived. A heater is switched off. A function is moved into another part of memory. Each solution preserves operation by making the remaining machine slightly more fragile and slightly more specialized. Engineers must understand what the machine was designed to do, what it can no longer do, and what unusual combination of systems may still keep it alive. The difficulty is increased by the age of the people and records connected to the mission. Many original engineers have retired. Some are no longer alive. Knowledge has had to pass across generations, from those who built the spacecraft to teams operating hardware created before they began their careers. A diagram drawn decades ago may explain why one circuit behaves strangely. A forgotten note may reveal that a backup system was tested only under conditions that no longer apply. Modern engineers work with archived information, computer simulations, surviving ground equipment, and the telemetry returned by Voyager itself. A thruster takes longer to produce the same movement. The symptom may come from one failing component, or from several systems interacting in a way never seen before. Testing different possibilities takes time, because every command-response cycle lasts almost 2 days. A repair that would require minutes in a laboratory can require weeks in interstellar space. A command sent too quickly can create a new failure before the old one is understood. Restarting the wrong subsystem could increase power demand. Changing attitude control could move the antenna away from Earth. Switching to backup hardware could activate components that have remained cold and unused for decades. It must continue flying, pointing, listening, and transmitting while the repair is attempted. Even the small thrusters used to maintain orientation have become a long-term engineering problem. Voyager must keep its high-gain antenna aimed toward Earth. Tiny thruster pulses rotate the spacecraft when its pointing begins to drift. Over decades, residue has accumulated inside narrow fuel tubes, reducing the flow available to some thrusters. The spacecraft compensates by firing them more often or for longer periods, but that approach increases wear and uses more of the remaining fuel. Mission teams have responded by switching between different sets of thrusters. Voyager 1 later faced another problem involving thrusters responsible for controlling its roll. A primary set had been considered unusable since 2004 after heaters inside the system lost power. The backup set continued doing the work for more than 20 years, but its fuel lines were also becoming clogged. Engineers returned to the old failure and reconsidered it. They suspected the heaters might not be physically destroyed. A change in the controlling circuits may simply have placed them in the wrong electrical state. If the cold thrusters fired before their heaters worked, the result could damage them. The spacecraft's star tracker also had to remain aligned closely enough that automatic pointing commands would not activate the thrusters at the wrong time. The team prepared a sequence designed to restore heater power and bring the dormant system back. A system regarded as lost for more than 2 decades became available as a backup, because engineers were willing to question an assumption made when no one expected the mission to last this long. The spacecraft survives because the meaning of its hardware is allowed to change. The same thrusters that once helped control planetary encounters now protect a radio beam carrying data from interstellar space. The same computer memory that once organized observations of giant planets now holds rearranged code needed to report plasma and magnetic fields beyond the heliopause. That limitation creates a different form of engineering. Modern spacecraft may carry flexible software, large memory, and powerful processors. Voyager carries very little of any of these. Its strength is that engineers know its systems deeply enough to find possibilities hidden inside a design that was never meant to operate for half a century. Each recovery also consumes part of the future. The spacecraft can be saved from one failure while moving closer to another limit. The mission adapts by accepting a smaller definition of success. At one time, success meant returning the first close images of distant worlds. Now, it may mean keeping one magnetometer active, receiving one readable engineering report, or maintaining a carrier signal through another year. A few measurements from Voyager may remain the only direct evidence from that region for many years. This gives engineers a reason to attempt repairs that would never be practical on an ordinary mission. Months of work can be justified if the result restores one instrument beyond the heliopause. Old systems can be studied again because every additional period of contact has scientific value. It follows electrical states and stored instructions. It responds to commands, points toward a guide star, and sends data toward the expected position of Earth. This creates a quiet difference between the machine and its caretakers. Voyager continues as though its procedures are ordinary. The team understands that every successful action may be difficult to repeat. A routine communication session depends on antennas, computers, thrusters, power systems, and memory surviving together. The mission can appear stable for months, while one hidden component moves slowly toward failure. If the transmitter fails completely, no other instrument matters. If attitude control can no longer point the dish, the signal will miss Earth. If the command receiver stops working, engineers may be unable to change the spacecraft's configuration as power declines. If a central computer fails in the wrong way, Voyager may remain physically intact while becoming unreachable. A machine that survived giant planets and interstellar radiation could fall silent because one ordinary component reached the end of its life. What makes Voyager different is the distance. Earth may receive a final incomplete signal, and then only noise. Engineers could continue transmitting commands for a time, hoping the spacecraft is listening. The Deep Space Network could search across nearby frequencies in case the radio system drifted. Antennas could listen near the expected position in case the dish remained partly aligned. But without telemetry, every attempt would be based on possibility rather than evidence. Its electronics might still contain small areas of activity. The generators would still release heat. Some systems could remain powered below the level needed for useful communication. Voyager will keep moving through the local interstellar medium at tens of thousands of kilometers per hour. The antenna may slowly drift away from the sun. The remaining warmth will fade. Radiation will continue passing through the structure. The spacecraft will become completely passive, guided only by gravity and momentum. Its path will carry it past distant stars over immense periods, though it is not aimed to enter any known planetary system closely. The instruments that once measured Jupiter, Saturn, plasma waves, and cosmic rays will remain attached, silent, and frozen. The probe will still carry evidence of the civilization that built it, but it will no longer send evidence of what surrounds it. This future is approaching slowly rather than arriving on a known date. Engineers can estimate how power will decline, but they cannot predict which component will determine the final moment. The spacecraft may operate longer than expected, as it has many times before. It may also encounter a failure no remaining workaround can solve. The mission has already exceeded its original purpose by decades and transformed from a planetary tour into humanity's first direct exploration of interstellar space. Its aging systems have returned information they were never specifically designed to collect, from a location their builders could not be certain the spacecraft would reach, while still alive. It is about extending a unique observation for as long as the remaining machine allows. The computers will stop organizing data. The thrusters will stop correcting the antenna. The transmitter will stop producing a signal strong enough to find. Earth will listen to the direction where Voyager continues traveling and hear only the natural radio sky. But the silence will not mean the spacecraft has stopped moving. It will mean that the final connection between the moving object and the world that built it has been broken. And once Voyager's aging electronics could no longer turn its journey into data, the spacecraft would enter the longest part of its mission completely alone, traveling through interstellar space long after Earth had heard its final signal. Voyager would not stop, fall, or disappear. There would be no explosion in the darkness, and no final image showing the moment the mission ended. The spacecraft would continue moving exactly as it had before, following a path shaped decades earlier by encounters with the giant planets. On Earth, antennas would keep listening toward the expected position of the probe. Engineers might search nearby frequencies, repeat commands, and wait through the long delay in case the transmitter returned. The spacecraft might still be functioning, but unable to point its antenna correctly. A computer could be trapped in a condition from which no remaining command could recover it. The radio signal might have become too weak to separate from the natural noise of space. The final transmission might not sound different from the thousands that came before it. It could contain a few lines of engineering data, one measurement of the magnetic field, or a simple carrier tone confirming that the transmitter still operated. The mission would end on Earth, while the object continued beyond the heliopause. When the computers and transmitter fail, the first will disappear, but the second may survive for an almost unimaginable length of time. There is very little in interstellar space capable of slowing it. The gas is thin, dust grains are rare, gravity from the sun becomes weaker with distance, and no engine is needed to keep the spacecraft moving outward. The probe will continue into the Milky Way, not toward a specific destination, but along the direction given to it by the planetary encounters that completed its original mission. It is moving faster than anything most humans will ever experience. Yet the galaxy is so large that its speed becomes almost insignificant. A mission to a planet has a moment of encounter. The target grows larger, Instruments become active. Images arrive. Years of travel lead toward a place. The darkness ahead will remain mostly unchanged. Stars will shift slowly in position as the spacecraft and the solar system move through the galaxy. The sun will become fainter behind it, eventually blending into the background of ordinary stars. The spacecraft will tumble slowly, carrying its silent instruments through an environment they can no longer measure. The machine that once depended on careful temperatures, stable voltages, and precise pointing will no longer need any of them. Voyager's importance does not depend on operating forever. It has already crossed the region where the solar wind ends. It has measured plasma beyond the heliopause, detected galactic cosmic rays, recorded the interstellar magnetic field, and followed disturbances from the sun into a place once imagined as empty. Voyager itself may become silent, but what it detected will continue guiding new models and future missions. The spacecraft has changed the meaning of interstellar space from an idea into a measured environment. This is one reason the mission feels larger than the machine. The interstellar mission emerged later, not because the spacecraft suddenly gained new abilities, but because it survived long enough to use old abilities in a new place. The same particle detectors that once studied giant planets began measuring the galaxy outside the heliosphere. The same radio system that returned close images of distant moons later carried faint plasma data from beyond every planet. The golden record attached to the spacecraft will remain under its protective cover. It contains sounds and images selected to represent life on Earth. Greetings, music, natural sounds, photographs, scientific information, and directions describing where the spacecraft came from. Space is too large, and Voyager will not pass closely through a known inhabited system. The Golden Record was created partly as a message to possibility. It acknowledges that the spacecraft may survive far longer than the world able to receive its signal. Someone would have to find the spacecraft physically, understand that the object was artificial, discover the record, and work out how to play it. Radio communication depends on precise pointing, electrical power, antennas, and people listening at the correct frequency. The spacecraft could travel through the galaxy for longer than humans have existed and never pass near anything capable of recognizing it. That possibility does not make the record meaningless. Its existence says something about the people who built the mission. At the moment Voyager was leaving the known planets, humanity chose to place a small description of Earth on the side of the machine. It is a limited selection created by one group of people during one period of history. The spacecraft carries evidence that its makers understood they were part of a larger universe and wanted, however faintly, to answer the possibility that they were not alone. Long after the transmitter fails, that intention will continue moving. Over very long periods, the surface of Earth itself will change. Continents will move. Species will appear and disappear. The sun will slowly grow brighter as it ages. They move around the center of the Milky Way along their own paths. Constellations that appear permanent during a human lifetime will distort over thousands of years. The record of that movement will exist only in calculations made on Earth. Astronomers can predict broad parts of the route, but precise knowledge becomes more uncertain across immense time. A tiny difference in position today can grow into a much larger difference after hundreds of thousands or millions of years. Voyager's path is therefore known most clearly in the near future and more generally in the distant one. It will pass within a few light years of other stars, but it is not expected to enter any system closely enough to orbit a world or be captured by a star. The Golden Record's cover was designed to protect it, but no one can know exactly how the entire structure will age across millions or billions of years. Interstellar space is gentle compared with a planetary atmosphere. Yet time gives even weak processes power. The spacecraft could remain recognizable long after its electronics fail. Its dish, booms, and main body may survive as a strange, artificial shape moving through natural darkness. For many thousands of years, the predicted location may remain accurate enough to describe its general path. Voyager will become less like a tracked spacecraft and more like a small artificial object somewhere in the galaxy. The two probes are leaving the solar system in different directions. Each carries its own golden record and its own history of planetary encounters. They are the earliest human-made objects expected to remain beyond the Sun permanently. Other probes are also escaping, but the Voyagers reached interstellar space while still able to measure it. That is what makes their final silence so meaningful. They will stop speaking from the very environment they helped reveal. Voyager's interstellar discoveries were not made through one spectacular image. They came through patient measurements of invisible things. The spacecraft showed that some of the most important regions in space cannot be understood by looking at them. The darkness beyond the heliopause appears empty, because human eyes are not built to see what fills it. Voyager extended perception into that darkness. Its instruments gave form to the invisible boundary around the Sun. They showed where one plasma ended and another began. They measured the galaxy pressing against the solar system. They detected the protection lost when cosmic rays increased. They recorded the Sun still sending disturbances across a border it no longer controlled. This was what Voyager found after leaving the solar system. Not a hidden planet, not an alien signal, not a sudden war marking the edge of everything familiar. It found a living boundary and an interstellar environment more connected to the Sun than expected. The discoveries are quieter than the myths surrounding deep space, but they are more important because they are real. Voyager taught us that leaving the solar system is not one moment. Gravity, particles, magnetic fields, and distant objects define different kinds of edges. The spacecraft crossed the heliopause, but it remains within the Sun's gravity. It entered interstellar plasma, but it is still near the solar bubble on the scale of the galaxy. It is outside, yet the Sun continues reaching it through light, gravity, and delayed pressure waves. The farther Voyager travels, the more those connections will weaken. Solar disturbances will become harder to detect. The Sun will become only one star behind the spacecraft. The heliosphere will shrink into an invisible region lost among the wider structures of the Milky Way. Voyager will continue toward no final edge. There is no nearby border, where interstellar space ends and something entirely different begins. The galaxy contains clouds, fields, stars, radiation, and enormous distances, but no marked road for the probe to follow. Its journey will become pure continuation. This may be the most unsettling part of the story. Human missions are built around goals. A launch begins the journey. An encounter provides the reward. A return or final transmission gives the mission an ending. Voyager will have an ending only for the people listening. For the spacecraft itself, motion continues. It will pass through the future without awareness, carrying a message from a world that becomes more distant every second. The record may never be found. The probe may never approach another planet. Its structure may slowly erode until little remains recognizable. Still, it will have crossed a line no earlier human object crossed while active. It will have carried instruments from the inner solar system into interstellar plasma and returned the measurements. That achievement becomes part of every mission that follows. Future probes may leave the heliosphere with stronger transmitters, more sensitive instruments, and engines designed for interstellar travel. They may map the boundary from several directions or travel much farther before losing power. Some may use sails, fusion systems, or technologies not yet built. Their designers will begin with a region that is no longer completely unknown. Voyager has already provided the earliest map. The map is narrow and incomplete. It follows only two paths. It cannot show the entire heliosphere or every condition beyond it. But exploration often begins with one line. A ship crosses an ocean. A probe passes one planet. A detector records one signal from an unseen environment. The first measurements do not finish the story. They make a larger story possible. Voyager's final gift may not be the golden record, or even its extraordinary survival. It may be the proof that a spacecraft can remain useful after every original destination has been left behind. A mission can continue because distance creates new questions. An instrument can discover something its builders did not know how to predict. A machine can become more valuable as its power disappears, simply because it has reached a place no replacement can quickly visit. Eventually, the deep space network will turn its antennas elsewhere. Other missions will need the time. New spacecraft will travel to worlds the Voyagers never saw. The direction of Voyager will remain in catalogs, archives, and calculations. Its signals will be preserved as recordings. Its data will continue being studied. The spacecraft itself will move beyond all communication. The silence will be complete, but it will not erase the journey. Thank you for spending this quiet journey with me. If you enjoyed exploring what Voyager detected after leaving our solar system, subscribe for more calm space documentaries and leave a like to support the channel. And tonight, here is one final question. If Voyager's last signal arrived tomorrow, what single message would you send toward the spacecraft, knowing it could never answer? Let me know in the comments. I will pin the most thoughtful answer. For now, Voyager is still moving through the darkness, carrying the memory of Earth beyond the sun's protective edge, while the space between the stars continues around it in silence. Good night.